So we have another wonderful exam to talk about. The subject, multivariable calculus. But it's even the best part of multivariable calculus. You see, it's the third exam where we're getting into integration, which really means we're going to be thinking about shapes, geometry. How do we describe areas, regions? And so we have a lot of beautiful, wonderful things to look forward to. And of course, as we always do, we want to start by putting down our name so that we make sure that we get the credit. And once that's done, we look ahead, 7 wonderful problems, so let's get going. Number 1, we have an integral, and it's actually been split up into 2 parts. So the first part is an integral where it says go from 0 to 4, and that's with the y, then go from 0 to root y over 2, that's with the x, of this function 5 over 4 plus x minus 4x squared. The second integral now says go from 4 to 5 with respect to y minus 4 to 1 with respect to x, and again the same inside, 5 over 4 plus x minus 4x squared. Say, all right, great. So we've got an integral. What are we going to do? Part A. Identifying equations of all the boundaries and the coordinates of their points of intersection, sketch the region of integration in the xy plane. Now we really have 2 parts, but this really should be thought of as one integral because the insides are matching. All right, so let's go through and do some dissecting. Now, the first thing to remember as we're looking at these problems is that when we talk about bounds, the bounds are really describing our regions. And remember that they match up, which is to say that the outer integral is going to match up with the outer variable. So, in particular, when this says 0 to 4, it means with respect to y. So secretly there's like a y equals 0 to y equals 4. Similar for this other integral. And then on the next layer down, same type of deal is going to happen. So that this is an integral from 0 to root y over 2. Again, this is like x equals and x equals. It's really crowded in there, but that's the idea. All right. So we have 2 integrals, so we're going to have to go through and do this twice. And all right, let's start with the first integral. First off, we say, let's see what the bounds tell us. The outer layer is telling us that we're having 0 less than or equal to y less than or equal to 4. The inner layer says we have 0 less than or equal to x less than or equal to 1/2 square root y. All right, good. So now we can start thinking about what's going on. When we think about the curves, we really look at the second layer, this inner layer here. So we're going between the curves x equals 0 and the curve x equals 1/2 root y. Now, oftentimes we don't have the easiest time of saying, wait, what is x as a function of y? It's the same philosophy, like, kind of like you turn your head 90 degrees. So instead we say, well, we could square both sides, multiply by 4, and then this is the same as saying y equals 4x squared. Okay, so we're going in between these curves. All right, now that's the first, and we're going to do our sketch all together. So let's get our second integral worked out before we go to our sketch. Okay, for our second integral, what's going on? Well, in this one, y is going from 4 to 5. Right, that's the outer layer. Now the inner layer. We have y minus 4 less than or equal to x less than or equal to 1. And again, it's this inner layer, which are the curves. So you have x equals 1 as a curve, and then y minus 4 equals x, which we can also say is y equals x plus 4. All right, so those are our curves. Okay, so now we're ready to start doing some sketching. Yeah, I know what you're thinking. This problem is a little bit sketchy, right? Well, okay, all right. I see your puns. So let's talk about our curves. X equals 0 and x equals 1. Those are pretty easy to sketch. So let's draw those. X equals 0, that's also known as the y-axis. And we'll have here x equals 1. I'm not trying to make this be perfectly to scale because I see that I need y to get pretty big. I'm not going to have it be perfect. Right now I'm just trying to sketch the curves. All right. Now, what are our other curves we need to look at? Well, y equals 4x squared. Okay, we can sketch that. And so that looks like a parabola. So y equals 4x squared. We were told to find points of intersection. We see some here. That's a pretty easy point to spot. Here's another one. This is at x equals 1 and y equals 4. All right. Now what about the other curve? Y equals x plus 4. Okay, so that intersects at 4, and it has a slope of 1. But of course, because our scale is a little bit strange, we'll have it not look like a 45 degree, but there we go. And again, well, we can spot that point. That's at 0, 4. And this point over here, that's at 1, 5. Okay, now let's shade in. So what are our regions? So for our first integral, y goes from 0 up to 4. So we're going between 0 and 4. So we're in between 0 and 4. And then it says that we're going to have x go from the left-hand side is this curve, 0. The right-hand side is this curve here. And so we have this part right there. So that's our region. It's a part of the parabola. And we'll go ahead, let's shade that in. All right, so we'll come in here, and we're shading, and we're shading. There we go. There's our region. All right. Now, the second integral. Well, what do we have there? Well, we're going now 4 to 5. Okay, so 4 up to 5. And what is our left? It's this curve, the y minus 4 equals x. Where's our right? It's that curve, 1. So we're going like so. So we're going, and we're forming that triangle. And again, let's shade that in. We'll grab a different color just to emphasize different integral, right? Okay, so now we have, those are our pieces. And together they make our regions. And let's see, have we checked all the boxes? We do have a sketch of the region. We've marked the functions, y equals x plus 4, y equals 4x squared, x equals 0, x equals 1, and we've marked all the points. Okay, good, good. So, great, we got part A. All right, and oftentimes when it comes to integration, the integrals themselves aren't the hard part. It's just describing that's the hard part. That's what we're really being tested on. Can we describe? Now let's go to part B. Write the integral. So when it says write I, it means this expression as one single integral. So it's like we want one integral to rule them all, right? Bring them all together. And we say, okay, what's going on? Well, let's put our sort of understanding here. See, currently what we can think of is that we're slicing in this sort of horizontal manner. Why did we have to break it into two parts? Well, we have to break it into two parts because there's a fundamental change happening partway through. So below 4 and above 4. So 4 is the place where we change. What's the fundamental change? We're changing the left-hand side, we're changing the right-hand side. When you have a change, you have to break your integral up. Okay, so we can't write it as a single integral with horizontal slicing then, and that's the whole reason that there are two integrals here. So we say, okay, so now let's change the way we slice. So we say, okay, well, what's our other option? vertical slicing. Yeah, we're going to go up and down. So that's what we're going to do. Now you might say, okay, will that work? Well, again, think about the shape. Do we have a consistent top and bottom? If the answer is yes over the whole range of values for x, then we're like, yeah, this is something that we can do. And you'll see that we do have a consistent top curve. This is that y equals x plus 4, and a consistent bottom curve, y equals 4x squared. So we are good to go in terms of writing it as one integral. All right, so here we go. So we're going to integrate, and integral, we're giving ourselves plenty of room here. The key thing is we're swapping our order of integration. So swapping the order of integration changes how you slice. The inside expression, no change. So we're still integrating this 5 over 4 plus x minus 4x squared. So that the inside hasn't changed. The way we slice has changed, so we have the dy dx. Now our bounds. Where does x go between? So now we're thinking of numbers. What's our smallest value of x to our biggest value of x? Well, conveniently enough, it's labeled in the picture. We're going from x equals 0 up to x equals 1. These should always be numbers in the outermost layer. Okay, so we're going to write at x equals 0, x equals 1. Now, you don't need to put the x equals, but I'm just emphasizing x equals, x equals. Now, the next layer, the y. Okay, where does y go from? Well, we go from the bottom up to the top. And because these are y bounds, we want y equals, which is good because we rewrote these in terms of y. So we're going to write it as y equals 4x squared. Now, again, you can probably just put 4x squared, and everyone knows what you mean. But this is emphasizing. We have dy, we want y equals something. Up to upstairs, y equals x plus 4. Now, that's the first part. We've now succeeded. This integral does the same thing as these two integrals combined. There's one more thing. We need to evaluate. Okay, well, can we do it? Initially, if we had to integrate this with respect to x, that's no fun. Too much going on there. But since we're integrating with respect to y first, this whole expression is treated like a constant with respect to y. So we say, oh, the constants are really nice, really simple to integrate. They're one of our favorite things to integrate. They definitely make the top 5 list, right? Okay, so we'll integrate. I'm going to go back to simplifying, just say 0 to 1. And now we've integrated. This is our constant, so we'll write that again. 5, 4 plus x minus 4x squared. And constant y. We're evaluating. And I do like to write the y equals. This is just so I remember for sure what am I plugging in to where. All right, so we're going to plug in these bounds. Okay, so this will be integral 0 to 1. We have our constant. Well, it's not a constant right now, but that same expression, 5 over 4 plus x minus 4x squared. Okay, then we take high value, x plus 4, and subtract the low value, 4x squared. And dx, okay, we barely squeezed it on, but we want to make sure it's there. They really care about notation, and so if you omit notation, they're going to get you. They are really like looking for every single detail on these problems. How do we integrate this? Well, let's take a second and ask, can it simplify? One of the things is, and you can almost always predict that this type of problem will be there, is that they're going to have something where you switch the order of integration, and by switching the order of integration, things get a lot simpler. So somehow we should get simplification. Look for cancellation. Well, here we have 4 plus x minus 4x squared. Here, x plus 4 minus 4x squared. they're the same thing. So what can we do? They cancel. And so this really is the integral from 0 to 1 of 5. Well, now that's not a bad integral at all. That's 5x evaluated from 0 to 1, which is 5. And done. There we go. The answer is 5. All right, good. So make sure you know how to do this one, because I don't write these tests, but boy, they love these problems. They love these problems. All right, one problem down. Let's go on and talk about the next one. Number 2. So D is a region. It's going to be a three-dimensional region, looking ahead. It's bounded below by the cone, phi or phi equals pi fourths, and above by the sphere, rho equals 3. So we don't have to guess too hard at what it looks like. There's this cone below, and there's this sphere on top. Okay, cool. By the way, when you see phi and rho, that should trigger, ooh, this sounds like spherical coordinates, because it is. And so there's a reason it sounds like spherical coordinates. Now, what are we asked? Set up, but do not solve, a triple integral to find the volume. All right, so let's talk about how do you find volume of a three-dimensional shape. Well, what you would do is you would do the integral over your region, which in our case is D, of 1 dV. The sort of the intuition being, okay, dV says you take your region, you split it up into little tiny pieces. And you say, what's the contribution of each piece? Well, it's 1 times how big the piece is. That's the dV. Say, okay, now add up all those little pieces of volume and you get the total volume. So what do we need to do? Well, 1 is really easy to handle. So we're going to have more or less 2 things we need to focus on. One is make sure we remember to put in the right dV. And then probably the bigger thing is make sure we know how to describe our shape in terms of the coordinate system that we're using. Okay, so to begin, let's do a sketch of our region. Well, we're in 3 dimensions because spherical coordinates tells us it's a 3-dimensional problem. And volume also says 3 dimensions. So, okay, so we are drawing 3-dimensional picture. Phi, let's start there. Phi is the angle off of the positive z-axis. So in other words, phi equals 0 is straight up. And so as we increase phi, we're going to be coming off of the z-axis. Now, how far off do we go? When we hit pi halves, we'll hit the xy plane. So we're only going about pi fourths, halfway in. So we get this type of shape. All right, so this is our phi equals pi over 4. All right, and there we go. We have our cone. That's our below surface, bounding below. Rho equals 3 says, oh, it's a sphere. Spoiler alert, they tell us it's a sphere. And what you do, it's a sphere of radius 3. So we're going out to a distance of 3. I just have to grab a pen here and say, okay, all right. So let's say that's distance 3, and we have our sphere going off. But we only care about that portion of the sphere, which is going to be above the cone. And so in particular, what we end up with is that our shape is, again, we have that cone on the bottom and that sphere on the top. Okay, so there we go. There's our region. Okay, so now we have to start thinking, how do we describe this? And, all right, well, let's talk about our coordinate system. Spherical coordinates. We have 3 things. We need to talk about our rho, our phi, and our theta. And where are they going between? So we'll do theta, because theta is actually pretty simple here. Now theta is more or less about spinning around the z-axis. And notice that our shape is completely symmetrical around the z-axis. So what does that tell us? Well, it tells us that, lo and behold, since we have complete symmetry, we're going to have theta goes all the way around. It's the same in any direction. So if you can spin, you have that symmetry on z-axis, it means theta goes 0 to 2 pi. What about phi? Well, we've actually had this conversation already, because what's happening? Phi equals 0 is straight up, and then we're going to keep going, and at phi equals pi fourths, we've hit the boundary of the region, then larger values of phi completely miss our region. So the only values of phi where we're hitting our shape are the phi's between 0 and pi over 4. All right, so we have 0, pi over 4. What about rho? Well, what is rho? Rho is talking about how you relate to the origin. It's sort of the r in polar coordinates type idea. So you say, okay, I start at the origin and I move out until I hit my surface that's bounding me on the outside. So I'm going from the origin out to the sphere of radius 3. So what does rho do? Goes from 0 to 3. So now we have our bounds. Cool. That was one of our two things. We also need the dv. And for this, do we remember it? So there's a song. And it goes, rho, rho, see, two rows, rho squared, rho, rho, sine of phi, d rho, d phi, d theta. Now, put it all together. Okay, here we go. Our answer for part A. We have the following. It's going to be an integral, integral, integral of 1. So we don't need to write down the 1. And then we have our rho squared sine of phi d rho d phi d theta. And now we just make sure we match. Theta goes 0 to 2 pi. Okay, so 0 to 2 pi on the outer layer, because the outer is theta. Next layer, the middle layer, that's attached to phi. Phi goes 0 to pi over 4. All right? Innermost layer is attached to rho. Rho goes 0 to 3. So this right here is describing our region in terms of inequalities. And now we have our answer for part A. There's the integral. We don't have to evaluate it. How do we know that? Because they told us. And we thank them for that. Okay. Part B. Cylindrical coordinates. Okay, cylindrical coordinates are a little bit different. Now it's not rho, phi, and theta. What do we have? It's z, r, and theta. So we have to talk about what's going on with these pieces here. Quick thing is we get theta for free because theta actually represents the same thing. So it's that, what's going on if you were to spin around the z-axis? Do we still have symmetry? Yes, we do. So we still have our bounds 0 up to 2 pi. Cool, 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 cool. While we're here, let's talk about our dv. We'll get that out of the way. And it has a bit different, as you can imagine. It is r dz dr d theta. This r is the same r that shows up in polar coordinates. So in polar, we'd have r dr d theta. And you should think of cylindrical as polar plus z. And so that's why you have that little extra piece. So what's left? We need to get our bounds for z and r. And once we have that, we're good to go. We'll be solid. All right, so how do we find it? Well, for me, I find the best way to find these things is to imagine doing a slice. So we're going to take this and slice it. And when we do that, what we'll have is we'll have here z, and then what we'll have here is r. So you might say, wait, do you mean x? Or do you mean y? Why do you call r? Well, because we have that same slice regardless of where we are, then I just say it's an arbitrary. Theta is arbitrary here. So what's the picture that you see when you slice like this? Well, we see two things. One thing we see is we see the cone. When we slice the cone, the thing that emerges is a line. And it's a line that's coming off at 45 degrees. And that's a pretty easy line to describe. That's the line z equals r. The sphere, what does that look like in the slice? Well, the sphere, if we slice, is going to look like a circle. Hits at 3, and it's going to come down. And so our region now, in terms of just this slice, is here. All right, so now we just sort of need to get some bounds going on, and life is good. So we should write down this formula for the top. Now, thinking as a circle, that would be z squared plus r squared equals 3 squared, which is 9. Solving for z, you get z as the square root, 9 minus r squared. Okay, now, one more computation. I know, I always say one more thing, one more thing. We can see where r is going to start at, 0, and we're going to go up to this point. Where is that? So it's where this circle meets the line. Now we can figure that out. So notice that here we have that z equals r and that z squared plus r squared equals 9. So you can imagine we can replace z by r. So that's r squared plus r squared equals 9, or r squared, because we can divide both sides by 2, is 9 over 2, or r is 3 over square root of 2. And we could simplify, but at this point we don't need to. Okay, so what does that say about our bounds? Well, to describe this, we're going to start by going with r bounds. Where does r go from? It goes from 0 up to this value 3 over root 2. So 0 up to 3 over root 2. Once I've picked r, where does z go from? Well, it goes between these two curves, which is z equals r up to z equals the square root of 9 minus r squared. And now, between these two parts, we can write down our answer. So we have the integral, 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 the 1, which we don't need to write again, the dv, r, dz, dr, d theta. Working from the outside, theta goes 0 to 2 pi. All right, great. Next layer, r, goes from 0 to this number, 3 over square root of 2. All right, great. Next layer, z. Z goes from r up to square root 9 minus r squared. And we're done. Wow, good, good, good workout. Really testing our knowledge of our coordinate systems and, of course, describing shapes. And all right, 2 problems down. Let's keep going. Number 3. We have a closed curve, and it starts at 0, 2, goes along the left half of a circle radius 2, centered at the origin, to 0, negative 2, and returns to 0, 2 along the y-axis. And then we're asked to find the integral around c, arctangent of x, oh, nice, minus x squared y dx plus y squared x plus 1 plus e to the y minus cosine y, not nice, dy. Okay, all right, all right. Let's step back. This looks intimidating, but oftentimes when you see crazy functions thrown in, they're sending you a signal. Don't try to do this the way that they're explicitly asking. Use your tools. Okay, so let's start by sketching our curve. So let's see what our curve looks like. We'll come here. So C is a closed curve. And by the way, the closed curve just means it starts and stops at the same point. There's another thing that says it's a closed curve. See that little circle there in the integral? That's around a closed curve. Okay. It starts at 0, 2. So that says x equals 0, y equals 2. So here's 0, 2. It goes along the left half of a circle of radius 2, centered at the origin, to 0, -2. Okay. And, all right, so we're going actually down below. So left half over here. And we're going to put an arrow. Orientation matters on these types of problems. And so now we have 0, -2. And then it returns to 0, 2 along the y-axis. Okay, so then we're coming back. So we're sort of tracing out the left half of a circle. All right, cool. Now, what do we see? Well, we have an integral around this nice closed curve, and we have this part. What's our tool? What do we have available to us? Well, there's something we have available to us, and it's called Green's theorem. So Green's theorem is this nice fact that says, hey, if you've got an integral, we'll write down what Green's theorem says, of m dx plus n dy, and that's right, so this is our m dx plus n dy, then this is equal to the integral over the region of the curve of, and this is always the part where you have to think for just a second here. And so let's think about this for a second here. This is going to be our, I'll tell you how I remember this. If I'm having a hard time remembering this, I come back to the curl formula. So you have I, j, k. You have your partial x, partial y, partial z. Then you have your m, n, p. You might remember this as curl. That might come up later. And what I try to do is say, okay, think about for the k part. So it's k, partial x, n. Okay, so that says I need derivative of n with respect to x. So that's n sub x. And then the other part will be this part going up. And that's because of the direction of the determinant part. That's going to be subtracted. Derivative with respect to y of m minus m sub y. So the moral here is it says, oh, I can transform an integral on the boundary to an integral in the region. Now you might say, why would that help us? Well, when we take these derivatives, the terms might simplify. Simplifying? Well, that's awesome. That's awesome. Okay, so this is, we'll put some notes down here. And so the reason why we did this is the part that shows up in Green's theorem is this part of the curl. Okay, so that's where this is coming from in case you're taking notes. All right, now let's apply it here. So we've got our closed curve, good. We've got our formula, good. One small technical thing to check out. Does the orientation match? Orientation matters. And so what does that mean? Well, for our curve and our region, what we need is we need to have things lining up. And this is the part of the course where we do the most singing. So what's the song? You channel your inner Beyonce. To the left, when you walk your curve, keep your region to the left, right? So imagine that you were standing here and you walked along the curve, right? So as you're walking, is the region on your left-hand side or your right-hand side? And if it's on your left-hand side, good, you've done it right. If it's on the right-hand side, then your curve is oriented the wrong way. What does that mean? You got to throw a negative in. But to the left, we're good to go. Okay, so we just check that, just in case. It's always good to be sure. Okay, so here we go. Our formula is going to say, I said our formula, but our problem, our integral is going to be equal to the integral over our region of, okay, so here, this is our n, this is our m. Taking the derivative with respect to x, notice that this part goes away. That's also a pretty good clue that you should take the derivative with respect to x. So that goes away, the derivative of 1 goes away, derivative of y squared x with respect to x is y squared. Subtract. Okay, now come here, take derivative with respect to y. Our tangent x goes away, derivative of minus x squared y with respect to y is minus x squared. So it's y squared minus x squared. And dA. Okay, so it's the integral over our region of, well, this is x squared plus y squared dA. Now that's a much, at least it looks easier, right? We don't have to stress about integrating arctangent of x. But we have to integrate it, right? We actually need to get an answer. Okay, so how do we do this? Think about the shape. What shape do we see here? Well, we see circle. What's a way to integrate circles in the plane? Polar. Okay, so we're going to switch to polar. All right. Wow. Probably didn't see that coming. Well, we should have been suspicious. If you see a circle showing up, yeah, polar might be involved. Okay, so integral, x squared plus y squared in polar becomes r squared. dA in polar is r dr d theta. Now, where is theta? Well, we're starting here at pi halves, and we're going to go, there's pi, all the way to 3 pi halves. So from pi halves to 3 pi halves. Where does r go from? Well, from the origin, we go out till we hit our circle. And it's the circle of radius 2. It even says it, circle of radius 2. Okay, so we're going 0 to 2. Okay, well, we're pretty much there. We've got our setup. And now we have things which are pretty straightforward to integrate. Still have to do it. So we have the outside, which we'll take care of in a second. And then r squared times r is r cubed. Integrate that with respect to r. Well, that'll become r to the 4th. And don't forget to divide by 4. Evaluate from r equals 0 to r equals 2. Now plug in 0, you get 0. Plug in 2, 2 to the 4th. Let's see, 2, 4, 8, 16. Okay, so that's 16 over 4 makes 4. So that's the integral of pi halves to 3 pi halves of 4 d theta. Okay, that's 4 theta from pi halves to 3 pi halves. Okay, plug in 3 pi halves. 3 pi halves times 4 will be 12 pi halves, also known as 6 pi. Plug in pi halves. 4 times pi halves is 2 pi. So 6 pi, subtract 2 pi, leaving us a final answer of 4 pi. So there you go. There you go. So this one is a Green's theorem problem. Know to recognize, look for closed curves in the plane. Make sure you have a good orientation. Know the formula. If you forget it, like I often do, you say, oh wait, that's the part coming from the curl. So I just have to remember the curl, apply it, and carry it out. There we go. Whew. All right. Well, another problem down. but still more than half the problems to go. Okay, so let's keep going. Number 4. We have m of xy is x plus 2xy cosine x to the fourth y squared, and nxy is y cubed plus x squared cosine x to the fourth y squared. Wow, crazy functions. And these do not look like very pleasant functions. They're not the kind of functions you want to take home to meet your family. But all right. Part A. Find the integral along curve 1, there's the C1, m dx plus n dy if C1 is the straight line from 4, 0 to 0, 0. Okay, so let's talk about this curve. So we'll sketch it really quickly. And we're going from 4, 0, so that's the point where x equals 4, y equals 0, and to 0, 0. And it has a direction, so we want to make sure we get the right direction. So we're starting here, we're going there, so we're going from right to left. Okay, so here's our C1. All right, excellent. Now, how do we do this? Well, this is definitely not Green's theorem. And we say, okay, well, what can we do? Well, what we can do is take a look and say, hey, you know, this curve is actually pretty simple to describe. What is it? Well, we can say that the curve looks like, well, how I would do it. I'll do it how I would do it, because how else am I going to do it? It always has y equals 0, right? Yeah, you're right, it does. And the only thing that's changing is the x values. So we're going from 4 to 0. So we could say, look, it's this curve t comma 0 from t equals 4 to t equals 0. So that's our description of our curve. And so, in other words, this right here is a parameterization. So we can use parameterizations to actually carry out line integrals. So we say, okay, so our integral of curve 1 of m dx plus n dy, well, that's equal to the integral, and we have to say where do we start and stop with our values. Well, we start at 4, and we stop at 0. So that's why this looks weird, because we're going sort of in the wrong direction. But that's okay, ignoring that small technical detail. Now, we're going to plug in to our m and n here. So in particular, let's talk about m of t comma 0, because that's what our parameterization says. Everywhere where you see an x, put in t. Everywhere where you see a y, put in 0. So it looks like t plus 2 times t times 0 times cosine of 0. Well, it's going to be hard to recover from that 0, so that becomes t. And then n of t comma 0, again, we're using our parameterization. What is that? Well, everywhere you see a y, put a 0. Everywhere you see an x, put a t. So that's going to become a 0 cubed. That's 0 plus t squared cosine of, well, 0 and t. So cosine 0. Well, okay, that's t squared. All right, so we have our m is t. What about our dx? Well, take the derivative. If x is t, then dx is dt. And then, what about our other term? Well, we have n, that's t squared, but dy, and what's the derivative? It's 0. So that just goes away completely. So technically, we could say plus 0, right? Plus 0, or if you like, it's t squared times 0 dt. But of course, that's out. So that's an integral we can carry out. Okay, so what do we have? We have 1/2 t squared evaluate t equals 4 up to t equals 0. Plug in the top, you'll get half times 0 squared, which is 0. Subtract 1/2 times 4 squared, leaving us with -8. Okay, so there we go. So we did the line integral by parameterization. All right, part B. Well, find a different curve. Same integral, but the curve now goes from the origin up to 0, 2. Okay, so what do we look like? We're going from the origin, so starting at 0, 0, and then we're going to x equals 0, y equals 2. And so we're going this way. So, okay, all right, should have maybe marked this point 4, 0. Here is the point 0, 2. Do we have a parameterization? Well, yeah, because we're only changing in one of our coordinates, we do have a natural parameterization that we can use. So, in particular, we can say this is the parameterization 0, t, where t goes from 0 up to 2. Okay, we're going to run through the same process. So the integral around the second curve, m dx plus n dy, is integral, and our parameterization goes from 0 to 2, so 0 to 2. We've got to do this computation. What is mt0? Well, okay, everywhere where you see, oh, not mt, 0, m of 0, t. Whoops! I got ahead of myself. I was looking here, should have been looking there. Okay, so everywhere you see an x, put it in 0. Well, see, there's an x there and an x there, so this is going to be 0 automatically. All right, hopeless to recover from that. All right, what about n 0, t? So everywhere where you see an x, put in a 0, so that part's going to go away, so we're going to be left with t cubed. So our m dx, well, we already have a 0, so that's going to become 0 plus n dy. Well, n, t cubed, what is dy? Since y is t, dy is dt. Okay, well, all right, integral of t cubed, 1/4 t to the 4th, and we're going to go from t equals 0 up to t equals 2. And plug in 2, we get 2 to the 4th, which is 16 times a 4th, which is 4. And subtract 0, because it's easier to plug in 0. And so I say, aha, the answer is 4. All right, great, great. Now, part C. Whew. Okay, so we want to find another integral. Oh my goodness, so many integrals. And what can we say here? Well, we want to find the integral m dx plus n dy if the curve is the part of the parabola x equals 4 minus y squared. Well, what is that? Well, it's a parabola, but it's been turned sideways. See, it's not y as a function of x, it's x as a function of y. So its peak is at x equals 4, and then it comes down. So this is the curve x equals 4 minus y squared. But we don't want the whole curve. What do we want? We just want the part of the curve that comes from this point to that point. So we're going from 4 to 0 to 0, 2. So what can we do? We could try to do it like part A and part B. Come up with the parameterization, figure out what happens when we plug it in, and just hope by golly things work out. It will not. We will fail. So we keep reading. You may use without verifying the fact that m sub y equals n sub x. Okay, we don't have to verify, but we have this nice fact. m sub y equals n sub x. What does that tell us? Well, it tells us a couple of things. There's different words we can use. It tells us that if we think of m and n as forming a vector field, that this is a conservative vector field. It says that there's a potential function, but it also says one really cool thing about line integrals. And so it says line integrals are, and I know you're already thinking it, what's the word? They are curve independent. So in other words, we only need to know where we start and stop. So as long as we have any curve that starts and stops at the same place, then we're good to go. So we can pick our curve. So here's the great thing. So see how curve 3 is going along the parabola? We can say, well, wait a second, we have other pieces here. So in particular, we really have three things. We have curve 3 up here. We have curve 1 down here, and we have curve 2 over here. So because we can switch out which curve we use, we have a great aha, which is to say the integral on curve 3 of our m dx plus n dy, well, we can combine, say that's the same as if you first went along curve 1, and then you went along curve 2. So that's what we have. So this is our great, do we understand what we get from the fact that these are equal? We get to have the freedom to pick our curves. Let's recycle. And we say, well, wait a second. We know what happens on curve 1. It's -8. We know what happens on curve 2. It's 4. So this is -8 plus 4, meaning our final answer is -4. And there we go. So this integral, which if we tried to do it as stated, so in other words, we found this parameterization, and we actually used that parameterization to do it all in terms of t, hopeless. But using the theory, we can do it. Whew. All right. Good. Another fun problem. And we're over halfway done. Whew. Okay. Now for a nice, gentle, relaxing back half of the exam, right? They always put the fun problems at the back. That's how they write exams. I'm pretty sure that's true. I read that somewhere. Number 5. So we consider this integral. It's a double integral where we have some region, x minus y times x plus y cubed dA. What's the region? It's bounded by the lines y equals 0, x plus y equals 0, x minus y equals 2. And we're told, using the substitutions, u equals x minus y, v equals x plus y, evaluate this integral. Okay, all right, good. So, what do we do? Well, let's think about what we have here. We're doing substitution of a problem involving iterated integrals, like, double integrals. Okay, so this should put into your mind, we're talking Jacobian, but really what we're talking about is saying, hey, there's 3 things that we need to handle. So let's make sure we go through and talk about the 3 things we need to handle. So every integral has 3 parts. And I would say the first thing you should look at is you should handle your dA. And that says, think about how you split things up. And this is the part that's related to the Jacobian. So we like to get that out of the way first. Once you have that, start looking at your function. So in other words, your function is going to switch. We're going from a function of x and y to a function of u and v. And the third thing you need to think about are your bounds. How do you handle your bounds? So every integral always has those 3 things. How do you break things up? What is it you're integrating? What's your region, which is your bounds? So when we're changing, we have to make sure we account for everything. Okay, so let's talk about our dA, breaking things up. Because as they say, breaking up is hard to do. Oh, no, it's not that bad. All right, so how do we figure that out? Well, here's how I like to do this. So we say, well, look, currently, when we think of this integral, because it's in terms of x and y, our current dA, we can think of it as dx, dy, or dy, dx. All right, no problem. And we say, all right, what we'd like to do is say, what does this become in terms of u and v? How do we figure that out? And so here's the nice rule. If I want to find du dv in terms of dx dy, I introduce the Jacobian. And so it's going to be a 2 by 2 matrix. And what goes here? Well, here's the nice thing about the Jacobian. It's super forgiving. So in other words, as long as you're close, it's going to work. And so technically there's actually an absolute value as well. It's an absolute value of the determinant. So that's one of the reasons why it's so forgiving. So we're going to take u and v as functions of x and y, and we're going to take their partial derivatives. So u sub x, u sub y, v sub x, v sub y. All right, so what do we have? It's the absolute value of u sub x is 1, u sub y is -1, v sub x is 1, and v sub y is 1. Now, what is that determinant? Well, it's 1 subtract -1, which is 2 dx dy. So we say, aha, we need to account for the 2. Now, here's a fun fact. Constants are super easy to account for. And the way you do it, just move the constant around as needed. You might say there's no 2 there. That's great. No problem. We can do it. And so in particular, what we're going to say, so this is part 1, we have this, is we can say, hey, our dx dy is going to be equal to, and remember this dx dy is really our dA, is 1/2 du dv. Now, by the way, we're not committed to going du dv. We can go dv du. But the important thing is we have this factor of 1/2. Okay. Now, the reason you want to do Jacobian first is sometimes it might peel off a piece of this. So some of this might get absorbed into your dA. So that's why you want to hold off before you go to your next step, the function. And since nothing got peeled off, we say, all right, we need to rewrite our function. And this is usually the fun part because it's the part that's not too hard. You say, okay, what do we have? Well, our function on the inside is x minus y, x plus y cubed. And we're looking for things in terms of u and v. So we say, okay, write things wherever you see an x minus y, try to put u. Wherever you see an x plus y, try to put a v. If there's anything left over, figure it out. Well, look, there's an x minus y. That's easy to spot. That's u. There's an x plus y. That's easy to spot. That's v. So our inside part is u v cubed. Now we've done part 2, the function. See how that was easy? That was great. Okay, now part 3, the bounds. And this, you got to think about this. Hopefully not too much, but enough. Okay, so here we go. We're on to the bounds, We must pay attention to the bounds. So, what are our bounds? Excuse me. So, we have 3 curves. So, it's a triangle. We have y equals 0. Okay, we know how to sketch y equals 0. That looks like y equals 0. X plus y equals 0. Now, notice you can write that as y equals negative x. Okay, so this is x plus y equals 0, or y equals negative x. All right? X minus y equals 2. Now, what's that? Well, that's the same if we just move things around. Since we're so used to it, that's y equals x minus 2. And I can already see I made some bad choices. Well, okay, so what's going to happen here? If we were to come down, what's happening is we're here at minus 2, and we have a slope of 1. So it's going to go through this text and then pick up again. So this is our curve y equals x minus 2. And now we say, we see that there is a shape that's been bounded here. So we have this triangle. Okay, cool. Now what we need to do is rewrite this shape, this description of this shape, in terms of u and v. And so we think about our bounding curves. And some of these are going to be straightforward, and some we'll have to think about. So let's talk about x plus y equals 0, this curve here. Well, notice x plus y has another name. It's right there. It's v. So I say, so this becomes the region v equals 0. Okay, well, that's simple enough. This x minus y equals 2. Again, x minus y has a name. That's called u. So we say, that's u equals 2. Great. And then there's one more curve. And that's y equals 0. And now we're like, there's not a nice thing for y, right? Because it's x minus y or x plus y. So don't panic. So now what you do is you say, okay, how do we handle that last part? Well, we think about our formulas. We have u equals x minus y and v equals x plus y. And now we say, okay, how can we combine these so that we just have y's and u's and v's? In particular, let's get rid of the x's. Well, we can subtract the first one, add the second one, and what would we have? We have v minus u, the x's will cancel, and we'd have a y plus a y is 2y. And so, in particular, what does this say? Well, if y equals 0, it's also true that 2y equals 0. And then that tells us, we need v minus u equals 0, or u equals v. Okay, so that's our other curve in the uv plane. All right, so let's sketch and see what we have here. Okay, so our region, we have some curves. We'll say u, v. We have the u equals v, or v equals u. Okay, that's easy enough. We have v equals 0. That's also not so bad. That's v equals 0. And we have u equals 2. And so we have a nice triangle shape. All right, so here's our beautiful triangle shape. And it's looking marvelous. Okay, so now we have our region. We should do one more thing with our region, which is we should make a decision. How are we going to cut this region up? So, are we going to slice up and down, or are we going to slice left and right? Well, looking ahead, let's see what's happening. So let's rewrite our integral with what we have so far. So our integral will become integral integral. We don't have the bounds yet because that ties to how we slice up. We do have the factor of a half, so we'll put that in. Our function is uv cubed, so we'll put that in. And now the question is, do we want du dv or dv du? So, in other words, is it better to slice vertically or slice horizontally? Or does it matter? In some sense, it doesn't matter. In another sense, we want to slice vertically. And you're like, why, Steve? Why are you like, I want to slice vertically? Here's the reason I look at this and say, slicing vertically is awesome. The reason slicing vertically is awesome is think about what your curves are. You're going from this curve down to the curve 0. 0 is a friend. And as often as you can get 0 involved, you want to do it because 0 will help you. Whereas if you were to slice horizontally, you go from this curve v equals u equals v, whatever you want to call it, to 2. 2, it's okay, but I'd say it's more of an acquaintance, not a friend. And so that's why we say, it's better to slice vertically here, and given that that's the case, that means we're slicing dv du. All right, so now let's look at our picture. Where does u go from? U goes 0 to 2. All right, that's our outer layer. Where does v go from? V goes from 0, see, that's why we like that 0, up to v equals u. And now we've done part of our steps, right? We've done the substitution, but now we have to carry out the integral. Okay, and we have a little bit of space. I think we have just enough to finish it up. But boy, they are not giving us a lot of space here on this problem. Integrate with respect to v. Treat u like a constant. So what we're going to do is we're going to add 1 to the exponent for v, so that's going to become a v to the 4th. We're going to divide by 4, so that'll give us integral 0 to 2. 1/2 times 1/4 is 1 over 8 u v to the 4th. Okay, so we've integrated with respect to v. Evaluate v equals 0 to v equals u. Now, plug in 0, you get 0. That's why 0 is our friend. Woohoo! Thank you, 0. Plug in u. Well, we'll get u to the 4th times u. So this will become integral 0 to 2 of 1/8, and u times u to the 4th is u to the 5th. Okay, so we integrate. Add 1, that'll be u to the 6, and then divide by 6. So 1 over 8 times 1 over 6 is 1 over 48. And we're going to evaluate from 0 to 2. So this is 1 over 48, which, on a side note, is 1 over 3 times 16. And then what's 2 to the 6? Well, that's 2, 4, 8, 16. Oh, wait, there's a 16. And then there's another 2, 4. So 16 times 4 is 64. Well, the 16s cancel, and that means that we're left with 4 over 3. And that's our answer. 4/3. 4/3. Okay, that's a good problem, right? So what are some key things to remember? When you're doing substitution, always make sure you account for the 3 things. Know how to handle your dA, that's where your Jacobian comes into play. Know how to update your function and figure out your bounds. The bounds can be one of the challenging parts. Also, remembering how to get that Jacobian in just the right way. It's easy to make a small mistake, so make sure you know how to get that Jacobian. So for bounds, draw your region, figure out your bounding curves, rewrite your bounding curves in terms of u and v, and say, okay, what does it now become? Once you know how you're breaking up your function, your bounds, you set up your new integral, and then hopefully it's not a bad integral to carry out, and life will be good. Whew! 2 more to go. Let's do it. Let's go for it. Yeah! Number 6. We're going to use a triple integral in cylindrical coordinates to compute the first moment about the xy plane. So there's notation here, mxy, for the solid in the region bounded above by this z equals the square root of 5 minus x squared minus y squared, and below by z equals 1, with the density of the solid given by density of xyz equals the square root of x squared plus y squared. Okay, we've got a lot going on here. Lots of words. First major thing we see is cylindrical coordinates. Okay, so cool. Now, the other thing that we see, and that we're going to need to make sure we pay attention to, is that we're looking for a moment. And so we have to make sure we understand that, and this is the moment xy. Okay, so let's pause for a second. No, not that kind of a pause. What we mean by pause for a second is like, let's recall moments. So how do we find moments? And so the idea here for a moment is to do the following. What we're going to do is we say, hey, the way you find a moment is you add up. So we're going to add. And what do we add? Well, there's going to be our mass and our distance. That's how you find a moment. So if you have something uniform mass and 1 point and you have a distance, that makes things easy. Now, for us, how do we find mass? Well, the way we find mass is we're going to do the following. We're going to have, I'll put distance first. So when we're talking about moment, there will be a distance involved, and we'll get to that distance in a second. And the way you find mass is its density times volume. Okay, so when we're setting up our integral, we need to make sure we understand these 3 parts: distance, density, volume. And in particular, the volume, that's actually fairly straightforward. And what is the volume? That's going to be our little volume. We think about breaking things up in little tiny chunks. It's our dV. What's our distance? Okay, what is our distance? You have to know what you're finding the moment with respect to. So that's where this xy comes into play. This is moment with respect to the xy plane. So let's do a quick sketch of space. And here we are. So I'm in my space, and I'm at a point somewhere in space. So hello point somewhere in space. And now I say, well, how far am I from the xy plane? So the xy plane, that's this part down here. Here's our xy plane. And so to figure that out, I say, well, the way I figure out my distance is I drop straight down. So what's this length in between? How do I find it? So the way you find how far off the xy plane you are is how much you move in the z direction. So distance is z. Now, what about density? Well, this will really depend on the problem, but we have density. We know we're moving to cylindrical. Cylindrical means polar plus z. So we're going to put on our polar hat and say, well, if we're in polar coordinates, x squared plus y squared is r squared. So square root of x squared plus y squared is going to be r. So our density is r. What does it mean to add up? Well, that means you do the integral over your solid. And that doesn't have a name yet, so we'll call it d. So we now say, okay, there's our formula. That's what we need to find. All right, good. So mxy is going to be the integral over our region of z r dv. Okay. Whew. Well, we're at the starting blocks, right? There's a couple things that are pretty straightforward. We are in cylindrical coordinates, so we know how to handle the dv part. That's a freebie. We should know that one. And so the dv, this is our r dz dr d theta. Okay. So now we have to talk about our region. So let's take a look. What do we have? It's the solid in the region. We're bounded above by this surface. Z equals the square root of 5 minus x squared minus y squared. Do we recognize this surface? Have we seen this surface before? Well, yeah, we kind of have. It's a sphere. If you were to square both sides, so if we had z equals the square root of 5 minus x squared minus y squared, this could be written as z squared is equal to 5 minus x squared minus y squared, or x squared plus y squared plus z squared equals 5. Okay, so it's a sphere of radius 5. Okay, so bounded above by a sphere of radius 5, bounded below by the plane z equals 1. Okay, all right, well, great, good. We're making progress here. So this is z equals 1 is our other one. So if we sketch again, we're in our space here. So what we have is essentially, you can think of it, we have a sphere of radius 5, and we're going to cut off the top. And that's the part we're interested in. So I think it might be called a cross cap. And so it's just sort of the top of the sphere. And so what it looks like is we have height 1, and we have this sort of disk here. That's the bottom, and then what's on top. Okay, so this, my picture is not the most convincing here, so I will try to illustrate and just say what we have. So here, this part is flat on the bottom, and it's sphere on the top. Now, it'll be helpful for us to see in a cross-section what exactly is going on. So if we were now to say, okay, what does this look like if we slice? Because we really should slice. And as we slice, we just imagine going shloop, right? You don't have to make the shloop sound during the test, but think about slice. What do we see? Well, we see the following. R and Z. And we have Z equals 1. Looks like this. And then we have this Z equals square root 5 minus R squared. Well, it's a circle. Here you have radius root 5, and it just comes down. So that this portion that we're after, it's really this piece here. We spin it around. All right, and we're almost there. We're almost there. What else do we need? I noticed that x squared plus y squared equals r squared. That's where that r squared comes from. There's one more thing we need, and then we'll be ready to go. The last thing we need is the answer to the question, where do they intersect? Well, all right. So for which value of r do we get that these curves, z equals 1 and z equals square root of 5 minus r squared, do they intersect? Well, we can just plug it in, right? We know z equals 1, so that says 1 is equal to the square root of 5 minus r squared. Well, okay, you can square both sides. 1 equals 5 minus r squared. Or you get r squared is 5 minus 1, which is 4. So where does it happen? This point here is at r equals 2. All right, here we go. So to describe our shape, z, r, theta, we need to set it up in terms of bounds. Because we have that great symmetry around the z-axis, that tells us that theta is going to have beautiful bounds. Beautiful, beautiful bounds, the best bounds. We're going to go full circle. So theta bounds are 0 to 2 pi. Now, come here to figure out your r and z bounds. That's why we slice, because it's easier to see. Where do we go with r? We go from 0 to 2. Where do we go with z? We go from 1, which is the bottom, to the square root of 5 minus r squared, which is the top. All right, so putting this together, we now have the following. This is going to be equal to integral, 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 zr dv. Well, the r's are going to combine, so we'll write that as zr squared dz dr d theta, and then use information here to fill in the bounds. Theta goes 0 to 2 pi. R goes 0 to 2. Z goes from 1 to square root 5 minus r squared. All right? Good? Got all that? Okay. And off we go. Because it's not just setting up. We actually have to compute. So the rest of it is now a computation, and so we're just going to patiently work it through. First layer, we're integrating with respect to z. So integral of z, treat the r like a constant. We'll introduce a half, and then we have 1/2 z squared. So we have integral 0 to 2 pi, integral 0 to 2, 1/2, I'll put the r squared, z squared, evaluate from z equals 1 to z equals square root of 5 minus r squared, dr d theta. Okay, can move this up. Now, nice thing is, we are going to square. Whew. The square root was making me nervous, but because we're squaring, that's going to help make it so we actually get a nice integral on the next step. Okay, so we're not integrating yet. We're still simplifying what we currently have. So z squared becomes 5 minus r squared, and then subtract 1 squared, subtract 1. All right. Now, notice here, this becomes really 4 minus r squared, and we're going to distribute through this 1/2 r squared. So this becomes integral 0 to 2 pi of integral 0 to 2. We still haven't integrated. 4 times 1/2 r squared is 2r squared. Then we're going to have 1/2 r squared times r squared. Don't forget the minus, so minus 1/2 r to the 4th. And we're going to do this dr d theta. Now we're ready to do our next integration. Okay, so this is integral 0 to 2 pi. Integral of 2r squared, that's 2/3 r cubed, minus 1/10 r to the 5th. Right, you add 1, divide by the power. Add 1, divide by the power. And we're going to evaluate r equals 2. So r equals 0 to r equals 2 d theta. Okay, which is the integral from 0 to 2 pi. Now, when we plug in 0, we get 0. Okay, good. Some good news. Plug in 2. Well, 2 cubed is 8 times 2. That makes 16 over 3. And then 2 to the 5th is 32 over 10. Well, the nice thing is, though, that you have a 2 here. And so you can get a little bit of cancellation. So instead of 32 over 10, it's 16 over 5. And so you have minus 16 over 5 d theta. This is a constant, and so we can go ahead and pull it out. And notice they both have 16. So this is 16 times 1/3 minus 1/5. And now when we integrate the rest, well, we'll get theta, evaluate 0 to 2 pi. Okay, we're almost there. We'll make it, we'll squeeze it in. When you plug in the evaluation at the end, you have theta from 0 to 2 pi, which means this will be a 2 pi. We already have a 16, and so 16 times 2 pi makes 32 pi. 1/3 minus 1/5, common denominator would be 15. So you'll get 5 over 15, subtract 3 over 15, which becomes 2 over 15. You say, okay, well 2 times 32 pi makes 64 pi, and over 15, and we have an answer. There we go. Whew, wow, like I said, it's a workout, but you follow the steps, and we fit it in. We got it all in on a page, right? And that included figuring out, oh wait, what is the moment? And making sure we got our bounds up, got everything set up, carried it out, and we made it through. Whew, and one more problem to go, so let's finish it up. Let's do that last problem. That brings us to number 7, our final problem. Woohoo! All right, so now for our nice cool down, right? So what are we going to do? We're asked evaluate the surface integral. So that's the surface integral. The dSA, little bits of surface. S is the portion of the sphere of radius 2 centered at the origin that lies in the first octant. All right, well, let's just remind ourselves. First off, what does the first octant mean? Well, the first octant is just another way of saying that x, y, and z are greater than or equal to 0. Sort of like in the first quadrant, that's where x and y are greater than or equal to 0. And so it's an eighth of things. The oct is kind of a clue. It's like an eighth of something. So I say, oh, okay, cool, 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 cool. So if we were to sketch, so we'll do a quick sketch here. We have our x, y, and z. And now what we have is, well, we have our sphere of radius 2. So we're going to go out 2 in our various directions here. So here we have 2, and here we have 2, and here we have 2. And, all right, and let's see. We'll draw. All right. So we have this nice little piece here. So there's our sphere. All right. So our idea is, of course, we're going to say, let's chop our sphere up into little pieces. Whenever you see, an integral, you're chopping things up. In this case, we're chopping up our surface into little pieces. And we're going to say, okay, what's the contribution from this little piece here? And then add up all the contributions, and life is good. The thing is, like, surfaces are kind of weird. How do we handle it? And so what we do is we say, well, let's think of it and say, let's try to get back to something we're comfortable with. What are we comfortable with? Well, we're somewhat comfortable working in the plane. So imagine, if you will, we have a flashlight, and we were to shine a light down on this surface. You say, okay, what shadow does this cast in the plane? Now, when we shine our light down, what will we see? We're going to see in the plane, we're going to see a quarter of a circle, right? Because it's just a piece of the sphere. And so now the real goal is to say, okay, we're not great with surface integrals, not yet. Maybe someday we will be. But we're kind of okay with two-dimensional integrals. So what we'd like to do is say, can we recast this in terms of describing our integral over this region in the plane? And so what's the question? How do we figure this out? Well, in particular, we kind of have to say, well, how does chopping something downstairs relate to chopping upstairs? So that's going to be a part of it. So let's talk about what we need to do. We have our integral. We're talking about the integral of our surface. And so we have the integral over our surface of z dsa. And now we have to say, okay, we're going to integrate over our region R, which is this part. We have to do a couple of things. We have to do something to handle here, and then we have to have something dA. And I want to explain what I mean here by these boxes. Okay, so box number 1 says we are going to take our function and rewrite it so it's ready to go. What needs to happen? Well, we need to make sure everything is in terms of x and y, because we're going into the plane. We want everything in terms of x and y. Sometimes we don't have to do anything, but today we have to do something because we see a z. All right, so to handle that, we start saying, well, let's think about our surface. How does z relate to x and y on our surface? And so we start by thinking about what's the formula for our surface. Well, for us, our surface is the following. It's a sphere of radius 2. So we say, well, we have x squared plus y squared plus z squared is equal to 2 squared. So that's 4. Solve for z. So subtract things. Z squared is equal to 4 minus x squared minus y squared. And to get z by itself, we'll take the square root. And because we only are interested in the first octant, we want z to be the positive square root, because we're positive. We say, all right, so this gives us a way to say, all right, what is z in terms of x and y? It is the square root of 4 minus x squared minus y squared. Okay, so that's what goes there. All right, now the more interesting part is the dsa, going to dA. It's not just a matter of 1 to 1. We have to take some additional things into account. So what comes in this box? And in essence, whether or not you can solve this problem or not solve this problem comes down, do you understand what goes here? I will say you probably would have gotten a couple of points if you wrote down just that part. But we don't want just a couple of points. We're after all the points. Got to get them all. Okay, so what's going on? All right, so here's sort of a quick formula for it. And we'll see if we can sort of do a quick bit of intuition about, wait, where did this formula come from? And but all right, here's the formula. So the rule is that if I'm trying to figure out the surface area, then it is the square root of f sub x squared plus f sub y squared plus 1 dA. You might say, well, what is f? This is your f. And now you might say, huh? What's this? Where is this coming from? Well, it came from class. We talked about it. We might remember it in sort of the following way, which is to say, if I'm at this point on the surface, I can talk about the tangent plane or the normal vector to that surface. Something to help me find the tangent plane. And so actually where this comes from is it's the normal vector, when you take it, the magnitude. So it's the magnitude of the normal vector to the surface. So you say the normal vector has the form f sub x, f sub y, and negative 1. So that's the normal vector, and you take the magnitude. So that's fx squared, fy squared, and negative 1 squared is 1. And then you take the square root. Okay. So we've got to kind of work this out. So this is going to take us some time, and we're going to be careful here. And so, all right, let's step by step, right? So let's start with f sub x. And we can note here that f of xy is 4 minus x squared minus y squared to the half. So according to this, we have the half comes down, and then it's 4 minus x squared minus y squared to the minus a half, and then chain rule says multiply by negative 2x. So that is the same as minus x over the square root of 4 minus x squared minus y squared. Okay, f sub y, very similar, 1/2, 4 minus x squared minus y squared to the minus a half times minus 2y, which is negative y over the square root of 4 minus x squared minus y squared. All right, so here we go. Let's see if we can move this up and be okay. So f sub x quantity squared plus f sub y quantity squared plus 1 is, square this part, that becomes x squared over 4 minus x squared minus y squared plus y squared over 4 minus x squared minus y squared plus 1. Now, if we wanted, we could add these together if we got a common denominator. So here we'll multiply by 4 minus x squared minus y squared, 4 minus x squared minus y squared, and when you add these all up, we end up with x squared plus y squared plus 4 minus x squared minus y squared, which means we have a 4 on the top and then a 4 minus x squared minus y squared on the bottom. Okay, all of this tells us what? Well, it tells us in our case, we need the square root of that. So what comes here is, take the square root. Square root of 4 is 2. And then downstairs, we have the square root 4 minus x squared minus y squared. So again, this part right here is that. All right? Okay, so that's the integral we need to do in terms of this region. We've put everything in terms of x and y. Now, fingers crossed, this simplifies. And it does. Whew. Okay, in particular, what do you see? The parts that are stressing us out cancel. Nice, nice. And so, in particular, after all of this, we come to the conclusion that the integral on our surface, z dsa, is equal to the integral over our region, which is this quarter of a circle, of 2. Well, we know how to do that. We don't even have to really think. If we're integrating, the 2 comes out, so this is 2 times the area of our region. And now we are like, hey, we know how to find area. In particular, it's 1/4 of a circle. So we say, okay, it's 2 times 1/4 of a circle. Well, what's the radius? Radius is 2. Well, okay, so that's pi r squared. So the 2 squared and the 4 cancel, and we're left with 2 pi. Done, done. So the actual integration was super easy, and that's the kind of problem I like. The hard part about this, and I am not going to sugarcoat this, it's not easy. The hard part is making sure you remember how to handle DSA. In particular, how do you turn a surface integral into an integral over a region, putting everything in terms of x and y. Okay, well, but the good news is we made it. We made it. We got to the end. All right, I know we took a while on this. We did go slow because we took time to explain everything. I don't want you to be stressing out because it's not going to help you. You can do this. You've gotten all the way to this point. Let's finish the class on a positive note. You're going to do great. I believe in you. I hope you do wonderful. And thank you so much for joining. And maybe I'll get to see you yet again. All right. Bye.